All right, so for my presentation today, I put an emphasis on part 2 test prep by taking some astro questions and building a presentation around kind of preparing for them, and then a quick little quiz game at the end. So hopefully we all do well on the quiz. All right, so if you want a writing utensil or a calculator handy, there's some light math on the quiz. So you can get that right now if you feel the need. Otherwise, you could probably do it mentally if you're with it today. So again, just a broad overview relevant to some practice questions I selected from a large compendium of practice questions. So first, I'll just highlight some generally useful information from a couple sources, mostly from Hall's Radiobiology for the radiologists. And the practice questions, again, from the Astro Radiation Cancer Biology Study Guide 2017 edition. So first, some background, radiation matter interactions. Ionizing radiation's importance in radiobiology is focused on the localized release of large amounts of energy to cause these reactive oxygen species and free radicals we've all learned about in radiation biology that require a certain amount of energy to even be created because an electron needs to be liberated. So these sort of reactive species then interact with the DNA and cause problems, leading to the mitotic cell death that we'll all kind of get through as this presentation goes. So the energy dissipated per ionizing event is about 33 eV. Recall 33.97 eV per ion pair in air. If we're talking just about like elements or bonds, so to liberate the electron from hydrogen, it's 13.6 eV, and the energy in a carbon double bond is around 4.9 eV for reference. So in terms of heat, the energy from radiation really is not very much. So the LD50 for humans is 4 gray whole body dose. This would be 67 calories in a 70 kilograms standard man, just for the sake of discussion. This equates to a temperature rise of 0.002 degrees Celsius. That's the same as just taking a sip of warm coffee. So obviously this energy is like, it's not like some sort of heat death, but it's just going to show that this energy creating these sort of biologic like results is the key that we need to take away here, rather than just the energy that's doing the killing. So chemical reactions taking place. Another comparison that Hall had was it's the same as lifting a person just 16 inches off the ground. So anyway.
That seems a lot harder than thinking about
it. Silly examples. But anyway, so the minimum energy to ionize different atoms, I just thought this was a nice frame of reference here. So again, most are hovering at or just below 10 eV, but obviously, some spike up higher there. But again, our targets really aren't going to be these elements kind of floating around in the body. This is just for a frame of reference. So a little bit more relevant to our discussion today, there are different types of ionizing events, directly ionizing and indirectly ionizing. So directly ionizing radiation is able to disrupt the atomic structure of the absorber, resulting in those chemical and biologic changes, whereas indirectly ionizing radiation, such as the X and gamma rays that we're all familiar with, give energy to charged particles, resulting in these same effects. So they have to go through that extra intermediary. The photoelectric process, again, dominant for KV energies. And again, if you recall the K edge, these sort of events are most likely near the binding energy of the target. In MV ranges, so what we deal with on a day-to-day basis, Compton events dominate. In the famous image on the right here, you can see that for the Z of absorber, around 8, anywhere in the MEV range is going to be dominated up to probably around 15 or 20 at MEV, where pair production starts to become dominant. And recall, pair production has a threshold of 1.022 MeV, and again, the contribution for that really is only significant above 15. So one useful parameter that you'll see in radiation biology textbooks a lot is D sub 0, pardon that not being a subscript, but this parameter represents a dose of radiation that induces an average of 1 lethal event per cell. So 37% of cells in a group that have been delivered, that have this D sub 0 delivered, will still be viable. So important number to remember there. Usually between 1 and 2 gray in mammalian cells. So this is kind of a good frame of reference for our standard fractionation number. A lot of these standard fractionation treatments are giving about 2 gray per treatment. And so you could think in terms of cell kill after each fraction, it'd be cutting the amount of tumor cells there down to 37% each time. Obviously, that's assuming no tumor cell regrowth, which is sort of happening as this goes along for these longer fractionated treatments. DNA lesions per cell immediately after this sort of dose. So this sort of 1,000 to 40 ratio between single strand breaks and double strand breaks is a good number to remember. And as we sort of focus our discussion a little further from here, these double strand breaks are the real killers, because there's no way for the cell to just sort of for sure know what was there if there's no reference on the other side of the DNA. So the DNA being this double helix, if there's just a single base removed, it can look at what was on the other side and reference that to put in exactly what should have been in place. Whereas if both are taken out, it kind of has to get creative about how it can even go about solving that sort of missing information completely. Again, single strand breaks are either repaired without consequence or sometimes result in mutation. This is just the cell's repair mechanisms not properly functioning, if that's the case. So those are really uncommon. You could think of that as just the on the order of just spontaneous mutation in a human or animal, not really likely to happen at all. So the interaction of 2 double strand breaks is what we really want to get at that results in cell killing. And these double strand breaks are induced linearly with dose. So free radicals and direct ionizations both cause these double strand breaks. There are many complex repair mechanisms. Something you'll see floating around in the textbooks a lot is this Rad 51. It's a recombinase that plays a role in homologous recombination repair. We'll get into the cell cycle aspect of that later. But during late S and G2, the sister chromatid is used as a template to fix the damage. So the cell is basically able to identify, hey, wait a minute, this DNA is just cut in half. There's a piece of missing information here. And based at looking up and downstream of where this break is, using the sister chromatid as a reference, which is not always the same information, because you're getting like, oh gosh, I'm trying to remember how to say this, but essentially, sister chromatids encode for the same thing, but they won't necessarily encode the same gene for that trait, sort of thing. So you could think of it as if there's like a copy from the mom and the dad or something like that. The dominant one will present itself for certain traits, and so that may get copied over. A piece of that information may get copied over if there's a gap that the cell is able to pick up on. I guess is the easiest way to think about it. Another key fact to remember, lacking oxygen will decrease the amount of DNA damage. So these reactive oxygen species from oxygen are longer lived, and so they're kind of able to drift further towards the DNA. One way to think about that is like, okay, like the target's a little bit bigger because we're trying to get after this DNA, and if these ionization events happen a little further away but can drift further, then it's still a hit. And also there are many drugs that can act as radical scavengers, and protect normal tissues in the area we'd be irradiating, but we're not going to get into that today. So again, keep in mind, targeting DNA here, events that occur elsewhere within the cell can still cause negative effects. They just take way more dose to be noticeable. So I can't remember where I saw this at one point, but the dose required if you just gave all of the dose to the mitochondria of the cell so that it was just unable to produce energy for itself would be thousands and thousands of times higher than the dose that already would have killed the cell if some of it happened to hit the nucleus. So other processes are going on, but DNA is the king. Homologous recombination repair, it requires the homologous DNA template, most likely following DNA replication in late S phase from the sister chromatid or in G2 phase. So this homologous recombination repair in this top image, Hall is showing us is occurring late in S phase or G2 phase right before mitosis. Right as things are getting replicated and the templates are open to be read from something that encodes for the same gene, just not necessarily the same trait. Moving on from that, aberrations can occur that kill the cell when repair is attempted. So these sort of aberrations on the chromosomal level, that being the dicentric and the ring, are two that will result in mitotic cell death. This is just a spontaneous death that occurs because the cell attempted to divide and was unable to. This is the big one to remember for radiobiology. This is the main killer. So I have some images on the next slide of these, but a dicentric is when there's two centromeres on the same sort of chromatid. So the cell will, after making all of these copies of everything, segregate them to the separate sides of the cell and then cleave down the middle to create two, ideally, viable daughter cells. But in the case where there's two centromeres, the cell has no idea where to pull that information because it could like end up pulling it in two different directions and then it gets stuck in the middle. It's really unable to segregate that information to a separate side of the cell because there are two centromeres. It gets confused, has no idea what's going on. And then that's a whole chunk of genetic information that would be missing from the offspring cells. Similar thing with the ring, better with an image on the next slide. And then another way for the cells to die during mitosis is the anaphase bridge, which is a chromatid aberration as opposed to a chromosome one. And those occur due to breaks in G2 phase. So real quick on the next slide here. So the first example on the left is just if a double strand break were to occur and information from sort of neighboring pieces of genetic information gets swapped over. And after replicating them, the the resulting chromosome there has two centromeres on it. In the middle example there is an example of how a ring would occur. Basically, two ends are cut off of the same piece of genetic information and they attach to each other, forming this ring. And during replication there, we have this ring and the knobs on the end created a line. And these acentric fragments do not end up with a centromere because they were separated from the centromere they were associated with earlier. So these acentric fragments at the bottom, they're just left behind. The centromeres are what are pulled to opposite sides of the cell. So again, huge chunk of genetic information missing, and the daughter cells just won't be viable. They won't have enough information to do what they need to do. And finally, on the end there, this is a, remembering the term, anaphase bridge, right. So when, in this case, say for example, the centromeres were able to be separated, but this piece of chromatin is remaining across the center of the cell. That's actually going to be so tough to break through that when this sort of like cleavage of the cell occurs due to proteins collapsing around the outside of the cell, they meet this and they're unable to complete the cleaving action successfully. So you could end up with two daughter cells that end up with a hole in them because the cell wasn't able to completely like cinch itself off, so to speak. So just three ways we can achieve cell kill during mitosis because of these double-strand breaks being incorrectly reattached to different things. One way to think about it is once you have a double-strand break, these ends have some free bonds, and you can think of it like they're sort of sticky. They're going to look for something else to be attracted to, because I believe it's hydrogen bonds across between the bases of the DNA, but I can't remember for sure. So Maya says yes, so, and she's the expert.
No. So I have a question. These first two, we call it chromatid, and the last one chromosome, isn't it?
So this is saying two different pre-replication chromosomes. So I think.
But the break is just happen at one chromatid.
Right. I think yeah. I think the like you're saying, this would be in a chromatid, perhaps more accurately. But this is ending up. It's a dicentric with the specific aberration here is the I think the chromatid, if I'm reading this correctly. So differentiating between chromosomes and a chromatid, I think this issue here is the chromatid in question that's like linked and stretched across the center of the cell. So I think that's how they're distinguishing the two.
Okay, so it's not that I thought that they just separated based on if you have chromosome and both chromatid is radiation, and then this one is just one chromatid, and then they will duplicate to make chromosome.
Oh, I see. So you're saying like how this is like two different pieces
Yeah.
of genetic information? Yeah. I think that may be specific to the dicentric, just because you need two centromeres. And I don't see how you'd end up with two centromeres from the same one. You could end up with a ring. So I think that is important to remember. So this is kind of from neighboring pieces of genetic information, not necessarily ones that were associated with the same centromere.
I'm gonna do badly on this quiz, I feel. I got one question. You said that these are all ways that cells can die. Would it be that would be apoptosis, though, right? It's not.
No, so apoptosis is a programmed cell death.
Yeah, but I'm assuming that these are problems that the cell would recognize and therefore correct the apoptosis.
I think it's mitosis
So-
because they cannot duplicate because they have error in them.
So part of what you're saying, I think I get to a little bit later, but the cells that die from apoptosis are very specific cell lines, and they occur like immediately after radiation. This is just spontaneous death while attempting to divide.
Got it.
Sometimes if you end up with daughters that don't have the proper genetic information after division, one of the ways they do die, you're correct, is apoptosis then, because they sort of are unable to encode for the things that keep them alive, and then that can initiate like apoptosis, breaking up into these apoptotic bodies, and it's a more well-ordered cell death, whereas these sort of ways are usually responsible for just a spontaneous collapse at trying to divide. So that's why these are classified as mitotic. Right. So, as indicated, the majority of irradiated cells die due to mitotic catastrophe. Cells attempt to divide and fail, or produce non-viable daughters. So some of those would go through apoptosis, but the majority, again, mitotic cell death. For a frame of reference, it depends on the type of cell, but human cells generally, if they're like regularly dividing, somewhere on the order of 24 hours is the cell cycle time. Again, it's going to depend on the type of tissue, like a reasonable amount. So like, and like obviously, nervous system cells really aren't dividing in the same way you would think of an epithelial cell as dividing. But so apoptosis can occur due to initial radiation damage in rare cases. So some examples, low-grade lymphomas, some myeloid and epithelial cells, particularly in the salivary glands, they pointed out as an example. But yeah, so often the mode of cell death, but still caused by issues stemming from mitosis. So it's less likely that the cell is just able to detect radiation and initiate apoptosis on its own. It's usually an issue caused from like a mitotic issue where it divided, didn't have, like I was saying, didn't have the genetic information it needed, and then decided it needed to die. So a lot of the time it is happening a bit later on. Again, cellular protein and organelle damage can occur, but it's really not happening on the order of damage that would be required to make a non-viable cell. It's all genetic information. So some interesting uses for alpha-beta ratios. So more useful than you might think. As I was preparing this, there were some practice questions that I wouldn't have known how to do, and they're relatively simple to solve. So just real quick, early responding tissues, somewhere around 10 gray for the alpha-beta ratio, whereas late responding tissues are somewhere around 2 generally. These parameters describe how cells die in a linear quadratic model. So this is the model that radiobiologists sort of landed on as their best approximation for experimental results. The only thing that they don't like about the linear quadratic model they ended on is that this curve is like constantly curving. This quadratic, this quadratic function is going to get steeper and steeper and steeper as it goes on. Whereas in reality, when you start approaching like multiple decades of cell kill, like multiple factors of 10 of cell kill, it approaches a linear function that we don't quite see. But again, most of the time we're not in clinical situations, we're not getting to the doses where it starts to like become more linear. And so the linear quadratic model holds. Also, they like that there's really only 2 parameters to play with, which makes it really nice for like modeling things. So these 2 parameters together indicate the amount of repairable versus irreparable damage that occur at different doses. So irreparable damage is given by alpha and then the dose delivered, whereas repairable damage is beta times the dose delivered squared. And then this little function here, you won't be asked to do any math with a cell survival curve like equation here. I would remember these 2 though. But anyway.
Sorry for interruption. Does anybody need egg? No?
Correct me if I'm wrong here, but isn't beta for double strand breaks? How would that be the repairable damage?
This
So beta is multiplied by dose squared, which indicates that it was breaks from 2 separate events not occurring at the same spot.
Okay.
So one other thing to notice, looking at these cell survival curves, always keep in mind that it's on a semi-log scale. So the y-axis is going to be logarithmic, whereas the x-axis is linear. So if you could ever ask any tricky questions about cell survival curves, like and how they're shaped and like describing the like math behind them, just keep in mind how the scales are. That's like a little thing for later. But anyway, so I will go through just a couple quick examples of problems I found without getting too thick into the math of it, because I think at least seeing an example or 2 with this sort of cell survival curve is useful, but it wouldn't have made a good quiz question. So in this example, they ask what the estimated surviving fraction of these famous Chinese hamster cells when irradiated with a dose of 5 gray, so surviving fraction for a 5 gray dose to hamster cells, and they give you alpha and beta. So all you need to remember is your exponential with the alpha and beta parameters up in the exponent, and then it's just plug and chug from there. So after 5 gray, only 10% would be surviving in this example. Little interesting nuance for the next question. They say, so same dose, but instead of delivered acutely, it's delivered over a 10-hour period. How would this be different? So the Astro Guide says, the repair of sublethal damage in this case implies that beta will approach 0. So many chromosome aberrations are the result of 2 separate breaks, but the cells now have enough time to repair these before the damage gets too bad. So delivered over a longer period of time, which this is interesting just for like to say if you were considering like LDR radiation versus like what we do at the machines, which is much more acute, how it's different. So the same dose is only going to result in 37% surviving as opposed to 10% surviving because it's given over such a long duration, the cells have time to repair as the radiation's happening. So quickly getting into fractionated treatments here. Fractionated treatments appear to be aligned, but they're on a semi-log scale, so it's really not properly described as linear. These fractionated treatments allow for healthy cells to repair themselves. And then this is just really easy to segue into the 4 R's of radiobiology. Paul says there's 4. I don't know. I've seen like as many as 6, but they get kind of redundant at that point. I don't really know why they start going much higher. But anyway, so with a fractionated treatment, your healthy cells are going to have time to repair DNA damage, and their DNA repair mechanisms are more properly functioning than in the cancer cells. So that's a net benefit to the person. Repopulation of healthy tissue. Again, the nearby healthy tissues, if any cells were damaged, they can divide and hopefully replace them. The cancer cells we want to target will redistribute within the cell cycle, meaning, okay, if the first time you shot it, it wasn't at the most sensitive part of the cell cycle, maybe the next time around it will be. And then reoxygenation. So as the tumor shrinks, hopefully more oxygen is able to get to the center of the tumor, and these cells will become more sensitive as a result. So you can kind of mentally classify it as things you want to happen to the healthy tissue by fractionation, and things that make your target easier to kill as a result of fractionation. Real quick, just a couple radiobiological concepts to get through here. So linear energy transfer is an average quantity expressing the average energy per unit length of track. In general, if it's heavier, it has a higher LET. Neutrons are very complex depending on the energy of the neutron. Perhaps more informative is the RBE, which this ratio indicates the amount of cell kill. It's the ratio of doses required to achieve the same amount of cell kill. So the kind of gold standard comparison is 250 kV X-rays. Fractionated doses can further increase the RBE, and the RBE will vary depend on the cell kill you're trying to achieve. I'll get into that in a minute. Some typical LET values. So again, as we get heavier, like these two giga electron volts iron ions, like floating around in outer space somewhere I don't want to be, would have an LET of 1000 keV per micrometer. But yeah, I don't plan on going to space anytime. Again, neutrons, we have this weird sort of track average versus energy average because it's a complex function of energy. Then LET for anything soft, like kind of X-rays or gamma rays, is going to be hanging out a lot lower than for these big, heavy, just bowling balls that are the heavy ions. So here's just a snazzy little graph showing that when LET increases, your surviving fraction of cells will fall off a lot faster. So just again, thinking of it as these are just wrecking balls flying through, taking out everything in their path, indiscriminate of what's in front of them. The alpha rays, they call them here, are going to wipe out the cells a lot faster than the X-rays would. And showing the effect of fractionation here. So for the same amount of, for the same surviving fraction, neutrons versus X-rays becomes a very different discussion when you start introducing fractionation. So again, this distance between the two is the RBE, and it's just key to keep in mind if you start introducing fractionation or the level at which you're comparing here, like the level of cell kill, these distances are going to change. I have another image for that on the next line. So the relationship depends on cell survival level being compared. So 0.8, 0.1, and 0.01 cell survival are being compared on this graph. And the relative biological effect versus LET of the radiation is like wildly different depending on which dose level you're comparing to. So don't need to know the nuances of it, just know that there's kind of multiple factors going on, even when you're just talking about the RBE, something that's pretty clearly defined within the equation. And then the oxygen effect, kind of got into that a little bit earlier for R's of radiobiology. Oxygen increases the number and overall types of free radicals available. So different species may be longer lived and able to damage DNA from farther away, kind of how I talked about earlier. So oxygenated cells are more sensitive to radiation. One example of a free radical that can form is oxygen reacting with hydrogen to produce peroxyl radicals. Don't need to know that specifically. But anyway, for the oxygen effect to be observed, oxygen must be present during exposure or within microseconds after the exposure. Now, ion pairs only exist for 10 to the minus 10 seconds on their own, and these free radicals exist much, much longer than them. The extent of damage depends on the presence or absence of oxygen. Again, kind of this larger target kind of analogy I came up with earlier. There's also the oxygen fixation hypothesis, which states that DNA will react with free radicals, and what normally would happen is a sulfhydryl group so could float on by and notice this sort of DNA radical like structure and reduce it back to the way it was previously. Whereas if oxygen floats by in an oxygenated cell and notices this DNA radical structure, instead of removing the radical to form its own sort of structure separate from the DNA, there's a hypothesis that the oxygen bonds with these radicals and stays affixed to the DNA, making it permanently useless for the cell, is one way to think about it. Hull doesn't really discuss this at length, so I'm not really sure what experiments they've done into doing this, other than the fact that oxygen making damage permanent, or like making the damage kind of affixed to the DNA is consistent with the fact that they say within microseconds there must be oxygen there, rather than being there as the radiation took place to sort of create more radicals and hit the DNA. The oxygen within several microseconds after is saying, oh, there's damage there, let me hold it in place, kind of thing. But again, not the most at-length conversation within Hall, and I don't really think it needs to be. And then one little quick note, the ratio of doses administered under hypoxic versus aerated conditions to achieve the same biologic effect is known as the oxygen enhancement ratio. All right, so now we can get to the more fun interactive part. It's kind of dense, kind of broad. Hopefully the questions are a little bit quicker to answer than some of those slides we're going to go through. So we're going to go to kahoot.it on your computer or mobile device. And when I create the game, there will be a pin for you to put in. Until then, just hang tight. A question will be presented to you. You'll have a short time to read it before the answers to the question will appear along with the question itself. and there will be some silly music playing, and it'll be about a minute before the end of the question. So, yeah, if you just go to kahoot.it, it should just say game pin, and that will only show up once I've launched the game on this computer. And you only earn points when you answer a question correctly, but you earn more points if you're faster. So there's this kind of dueling incentive to be fast, but also still be correct. And so there will be 17 total questions that I took. Oh, it'll also show a leaderboard between questions and at the very end of the game. So if you want to come up with a silly name, you're welcome to, as long as it's work appropriate, I guess. But anyway. All right, so here is the game grid.
I don't know who am I.
Do we have everyone?
No.
I think we're still waiting for Kingsley.
Oh, yes. Who's missing?
I was assuming
Wakey, wakey.
No, I answered Kate.
Oh.
We should not say.
Kingsley, are you able to join? All right,
Oh.
I
cool.
want to.
All right, so I think we have everyone and we're good to go. Right, here we go.
Oh boy. I made the wrong one as well. I did it really fast.
Yes. No.
I should have been diagnosed
All right,
Nice.
confidence scattered. All right, very good.
My, you are the first
Oh,
not even know.
Oh, no.
one. No, actually.
right answer. He was a real person.
Boston icon.
Oh.
Oh.
What?
50 is not an odd.
It's the closest. So recall that graph during the presentation.
It wasn't.
It was showing at or just below 10 eV for an atom.
You're
Yeah.
thinking of air.
All right.
Ooh.
Oh.
I enjoyed this one last.
Mike, you should do it fast if you want
I-
to keep
I had to read all the answers. There was
You
just
should
one.
use-
get it wrong.
Yeah,
All right,
if
everyone
you-
got that
If
one.
you lose the time, then you cannot stay
I
at
know. I
first.
wanted to read all the answers.
The K edge.
Oh,
Oh, Aaron's on a hot streak. 3 correct answers in a row.
eating up.
All over.
Oh.
This one was tricky. So Rad 51 is involved with the repair of double strand
Yes.
breaks.
Okay.
But the yield of double strand breaks upon radiation, it doesnn't matter if Rad 51 is active or not. So
It should be after.
right, so Rad 51 does the fixing after the fact,
Yeah.
but this question is asking more specifically
Why?
how many double strand breaks will occur. And the ability to repair has nothing to do with how many were created. And amifostine, if anyone was curious, is, I believe,
Sensitizer, right?
yeah,
Sensitizer, yeah.
Didn't they get like astronaut or something? Or-
Oh,
No, maybe it's
radio
the-
protection.
maybe
This
it's
is
the
a-
protect-
That's what they get.
this is right, this is a scavenger. So it scavenges
So it's
the
protected,
free
okay.
radicals in the cell, in the healthy cells.
So
So
it's protected.
yeah, so that's a protector. So tricky question.
Nice.
I narrowed it to green and yellow.
All right, so again, the nucleus has all of this sensitive genetic information and
I
controls.
pushed the wrong button.
The mitochondria is the powerhouse, so.
The mitochondria is the powerhouse of the cell, but not quite as important as the nucleus.
I just
It's too
learned-
slow.
Aaron.
Too slow.
Yeah.
Right,
I was looking for G2.
right.
For
It's light S or G2 would
Oh,
both be
yeah, I
acceptable
just
answers,
had
but we didn't have a G2. So,
Oh.
Aaron, 6 straight.
Yeah, he's quiet. He just can't.
I forgot to tell you guys I'm cheating.
Yeah, Aaron's got the escrow quiz pulled up.
Right, so the dicentric is a chromosomal aberration. The anaphase bridge is a chromatid, I believe.
Yeah.
They
Yes.
classify it very slightly differently.
That's what I could.
Oh, well.
Oh.
All right.
It was too late. Too late.
S and G2 phase. So, yep. Again, these chromatid aberrations we're talking about most likely to occur where the DNA is being replicated.
Oh, yeah.
Yeah.
I think I did the same thing.
Mitotic catastrophe.
I'm not stupid.
Never mind. I did the same thing. After I did that, I reread the question and thought that I had it backwards.
Yeah.
All right.
He's coming.
He's back on the leaderboard.
Our call to come back.
These astro questions were pretty good.
This was not coming. Oh, shit. I don't.
This definitely was covered, Rico. I'll show you the slide.
No.
Oh,
What a guess.
all right.
I mean, yeah, some of them didn't make sense.
Yeah.
So no one picked this one, which is good because I don't know. Apparently, in their explanation for this one, P53 does something upstream of back and backs. So we all should have known that. But anyway, so
What was P53? We had it RB and P53 is something.
P53 is the Jesus gene, like the savior.
Yeah.
It causes apoptosis without radiation.
Okay, yeah.
Not good.
Yeah, it's like if you're missing P53, you're almost guaranteed to get cancer in your lifetime and die from it.
Oh, because you
Oh,
don't
it's
have the ability.
it's a tumor suppressor gene then.
Yeah,
Yes,
it's like the
it's like
primary.
RB retinoblastoma.
Yeah.
RB is also like,
You have 2 copies of it, and I think if you're missing one of them, your odds of getting cancer are crazy high.
What have you got? No.
Then you're going to die. Probably pretty
Next
young.
question. So if you took notes, you'll be remembered. So the alpha beta ratio equals 3 gray. Irreparable and repairable damage, if you remember the equations. So alpha.
it's 2.3 times B.
Yeah, I just hit the wrong one, sorry.
I wish I could have it like that.
Yeah.
Do that. I don't know. Which one? Whatever. Oh,
Yeah, it's because alpha beta is 3.
I can't solve it. How can you solve it?
It's the ratio of 9 over 9 squared, which is 9, and then the alpha beta is 3, so it's a 1 divided by 3. So 9 over 3.
Oh.
But I still hit 1 to 9.
Jimmy got it wrong and knew exactly why. Alright, so that was a tricky question. So
1 cup, 3 to 1.
Who's the one that got it? Was it Aaron? Is he still?
it had to be Aaron.
Yeah, he's concentrated. Don't practice.
No, definitely wasn't me. I lost my streak on this one.
Oh, that's why I asked.
Someone up the leaders. All right. So we'll see.
Oh.
This was a bit cheeky to do this.
No, that's not very good. We should do it on 5.
Pretty sure I just did it backwards again.
I was tired of
I
this
did it.
question.
I did it.
Good job, everyone.
Shoot.
Could have been a guess because 2 and 10, but right on.
How many more is
4, 3, 7, 5 more questions.
No, dull shapes.
what?
So it's an
What?
semi-long.
I'm very proud.
It's a semi-long plot, and so the fractionated when it's a line
You
on
mentioned.
a semi-long plot, it's really an exponential.
You fail as a teacher when no one in the class gets
I was like, how could I say this without saying, this is a quiz question?
Yeah, you mentioned.
Who said linear?
I will admit I did say linear, but that's because I'm answering this on my computer. I will say I didn't mean to hit linear quadratic, so I would have got it wrong anyway. But I hit the wrong button.
But lucky.
Right. So, right, it does make a line, but it's on a semi-log plot, so it's really not linear.
But you didn't mention.
It's a tricky question.
You did.
All right, next one.
Space ions.
Oh, this one's
Oh, come on, really? Just when you think you find the definite one.
Gotta know your periodic table on this one. This one's tricky too.
yeah, but it's the energy difference. That's like the hard part. Is that a big enough difference?
Oh.
Nice.
So it's the argon ions.
What is next?
How am I supposed to know how big argon is? Come on.
It's all the way over here on the other side.
It's way on the side.
What is it up high? Is
I'm
it
like,
down
it's
low?
probably like 2 to 3 times bigger. 75 versus a now.
So Astro really asked this question?
Yes.
What?
So what is next? Is it carbon?
I think carbon is
How do
second.
you calculate it? What is the equation that takes into account mass and energy? What is the relationship?
LET?
Yeah.
Is it like
Isn't it-
S?
It
Is
goes
like the
LET goes up with mass, it goes up with energy, but how? Are they both linear?
So can you use the S, like S, the second power?
I guess because they're ions.
Yeah, so if we can use a second power, a second
What's
power.
the beta block formula? That's probably got the exact one of these you want.
And that's
This was a tricky question, so good job to those of you who got it right.
I think the problem is
The size of the ion is a very big
Clearly,
factor.
it's a huge factor.
It's a huge factor. It's the takeaway from this question.
I think it depends on positive charges squared.
Positive charges squared does sound familiar.
Yeah, because eventually that's going to impact on Coulomb force, and then that's going to play into your solid power.
Yeah.
Z squared divided by B squared.
It's
divided by D.
PETHE if you want to Google it.
All right, I can Google it real quick.
BATHE.
Like this.
THE. And then hyphen block. I'm pretty sure it's BLCHAE. Yeah, try that. It'll
Equation.
do it.
Oh, that's all we have to do.
Yeah, we can just look at 4 pi z squared over the rest mass
We don't
energy.
need all of them.
So z squared, I guess, is the
Z squared.
Yeah.
So mass.
Z
Goes
squared,
with Z
but the,
squared.
yeah, we just use C squared divided by B.
So it's
energy.
probably linear with energy because it was Z squared, so it was argon because the argon was more important than the energy.
Yeah. I could look up the exact explanation of this. I have the answer slide somewhere, so I can pull that up.
Argon was the heaviest thing on Earth.
Yeah.
yeah.
There were more atoms.
So mass, very important.
Not mass, charge,
Charge. Yeah.
despite getting it wrong.
So this one's really tricky. So I suspect those who said equal were probably thinking, oh, well, high LET radiation really isn't going to care about oxygenation very much, so it would be equal. But remember, you're comparing to 250 keV X-rays, and though the amount of cell kill achieved by those is going to be affected by the aeration of the cell. So there's like multiple layers to this one. So the RBE will be affected because the reference radiation will be affected by the aeration. So
I'm starting to see why a lot of radons don't like astro.
What kind of course was this to test stuff then? Is it like a 1-year like PhD in radiobiology? Yeah. This is so Even if I've done the radiobiology class yesterday, I don't know. We're not gonna pass
no
exams.
movement. All right,
We got
this is
there.
great.
Here we go. The last one. That's what I read everyone.
Yeah, they're every time I was typing in either a question or an answer into Kahoot to make this quiz, it kept warning me like, player experience is much better with shorter questions and answers. Like it throws up a warning because I have very long questions and answers.
We have a streak of 1 right now.
I also like how he continues to say that Eric has a 10-win streak.
Just going for it.
Yeah.
All right.
So yeah, to achieve the same amount of cell kill.
Even the answers are all really tricky. Like
Yeah.
even if you kind of know what the answer is, all of the answers are like you can't rule out some of the easy ones.
Yeah.
Like none of them are like really obvious. Like
Yeah, I went with blue and I'm like, well, if I give 200 gray in one dose or something, it doesn't matter.
So yeah, I would say I guess the kind of loophole that really isn't a lot of test questions for OER would be like flash dose rate, where they're just like irradiating
Yeah.
so fast that oxygenation doesn't matter.
I can see
But
blue.
that's, I mean, in conventional therapies, I guess, for most.
I can see blue being wrong as well because it's not a definition. It's just a true statement with it probably.
if you get this as like you know when you're in an elective and you get this exam, you have to do it on your smartphone to get the points. You don't get your accreditation.
Participation.
There would be people storming out of this room because of the answers. Like, yeah, that answer is also true in certain circumstances.
So yeah, I tried to pick the easy ones. Like a lot of these talk about biology. I'm like, there's no way I'm going to be able to learn this myself and then teach it to other people. So
That was the last one, right?
yeah, those are the last ones. So we get to see who the winner is.
That makes a lot
The
of
podium.
Another podium.
Here we go.
What a suck.
Hi.
Hi.
Me.
Come on. Hey, Rob.
You told me I was 12 points behind you.
Oh, Mike is almost.
Almost made the
Almost
podium.
there.
Aaron, where did you learn radiobiology?
It was East Carolina for a semester of nothing, and then to learn it myself being here. So
I think it also tells me how good I am at teaching afterwards.
With the exception of that one question.
0% correct.
Yeah, so I had 4 difficult questions. Yeah,
Can we see the answer of that? Can be there. There as well.
oh,
Yeah.
this guy?
Yeah.
Okay, so I think if I remember how to work it out, it'd be something like this. So. Alpha root theta equals 3, and then dose equals 9.
Yes.
So you have alpha d is the one parameter, beta d squared is the other, equals 3 beta d, and then you just plug in 9. So 3 times 9 for this equals, yeah, I'm canceling out betas, sorry. And then this is 9 squared. I think. Am I thinking that right?
3 to 9 or 1
Yeah.
it'd be 9 squared divided by 9. It'd be 9 squared divided by 9, and then the ratio would be the alpha beta ratio.
So yeah, 3/9 goes to 1/3. And then you just have to remember which is repairable versus irreparable. Man. So yeah, that's a tricky one. I can look up the LET one, see if they have a reasonable explanation. Let me go grab my laptop.
It's like 5:30 on Friday, I'm satisfied with your hour. That was fun. Have a good weekend, all.
All right. Yes. Oh, there we go. And that was for the heavy ion one.
Yeah.
Their explanation. Clinically relevant 75 MeV per nucleon argon ions have LET of 250 keV per micrometer. And then
250?
yeah, 250 keV per micrometer. And then the 1 GeV nucleon and the 18 MeV per nucleon carbon ions have LET values of approximately 10 keV and 108 keV.
Oh.
Respectively. So they don't even give like the physical explanation, they just say, yeah, it's just higher. You should know the number because you're going to get argon therapy in your clinic.
So, but the normal one is 0.3 kV per micrometer, like the X-ray.
Photons.
Yeah.
I think they're only in that range, right? In order of like.
Yeah, like
That's what it said that in your slideshow, right?
yeah, I think it was up to 2 or something,
2?
maybe. Let me go
Because
back.
alphas are like 10, aren't they?
Yeah, alpha's somewhere on there. Let me see. This is what Hall says. So 250 kV has like more LET than like the cobalt 60, but they're like, a couple. And then the space ions that I thought would have been a much better answer to that question is very high. But anyway, thanks for playing, everyone.
Thank
was
you.
fun.
Yeah.
Hope you had a good time.
Let's do that more.
that's-
Always your questions.
Yeah.